Okay, good afternoon, everyone. So we'll continue with this problem we started discussing yesterday. Now, yesterday I showed you the formulas that I have come up with. However, it would be a good practice to actually know the standard things also. Okay, so please let's discuss that also. Uh, Once you are familiar with some of the standard things, then you can freely go ahead and discuss this. I mean, use the formulas that I shared. Now, see, uh, and another motivation is to see that is to show you that when you actually use the standard method, how painful it is. Okay, so you have to help me out with one thing. So yesterday we had found out the moment. You tell me the values of the moment vector. So from yesterday. So what is this moment vector? This is the moment vector which is balancing the moment due to these forces with respect to this point. So you first find out the moment of these forces with respect to this point, and whatever will be the counterbalancing moment over that cross section which is exposed, that is what I am writing here. Okay. So tell me the values. Minus 28.125 I had. Minus 63.75 J had. All minus. Minus? Only 75. I have a suspicion that is slightly wrong, but no, it is not wrong. Huh? 21. 281.25. Acha. 28 only. Okay, 28 only. Okay, ठीक है ना? Okay. Other values, see, it doesn't really matter how much those values are. At least the minus plus, if it is okay, it's fine. Okay. Now, what we are going to do is, we are going to place we as the observers, as the solvers of this problem, we are going to go and stand over there, and we are going to look into the x-axis. Okay, we are going to stand over there and look into the x-axis. So, what will this thing look like? The cross section will look like this, where this is our y-axis, this is our z-axis, and coming out of the plane is the x-axis. All good? Now, identify the point A. This is our point A. And identify the point B. This is our point B. These things should be absolutely clear. Don't make it left, right, all these things. Okay. Now, one by one, we'll do the things. So, first of all, at the point A. For the point A, so in all of these problems, usually they will be set up in such a fashion that you will have to find out the normal stresses and the shear stresses. This is the usual thing asked. In addition to that, some other complications may be given, like at this location, you find out the state of stress and then you find out the principal stresses. Those things can be given, but those are further post-processing. The first thing that you have to figure out is the state of stress. Now, for A, there will be one normal stress. And now this normal stress is what? When I am referring to this, what subscript should I write? Sigma XX. Sigma XX, okay, sigma XX. All right. So this is sigma XX. Now, if I want to write the tau, the shear stress, I will have a tau xy over here. Okay, I will have a tau xy over here. I will also have a tau xz. Okay, so both the things have to be accounted for, tau xy as well as tau xz. Similarly, when you go to point B, there will again be a separate sigma xx. There will also be a tau xy here. There will also be a tau xz here. Whether they are zero, non-zero, we'll see later. We'll see later, but in general, this is the setup. Okay, now we have to fill in the blanks. Now, like I'm trying to deliver to you in a very structured fashion. So in tau xy, there no, step by step. Tau xy, there will be a contribution from torsion as well as the transverse shear. Okay, so have this setup in your mind. Within each of this tau xy and tau xz, there will be a contribution from the torsion. There will be a contribution from the transverse shear. Okay, so TR by J and VQ by IT. These things should be there. The game is to actually understand clearly which of the components here will contribute to what, and along with the proper sign and sense. Okay, for all three things, the sign and the sense are very important. Okay, for sigma xx, whether you are calculating for point A or point B, if the sign comes out wrong, even if your magnitude is correct, it gives a completely wrong indication for the design problem. Why? Because positive means tensile and negative means compressive. Okay, they are like literally worlds apart. Okay, or poles apart. So one by one. Now for sigma xx, you tell me what are the things that are going to be important at the point A. First, the most, like the easiest thing. Okay, the easiest thing is what? Force by area. Okay, the normal force by the area. Now let us also write down the normal forces. So the F, what is this F? This F is the negative of these forces which are there. These are the applied forces. If I go and look over there on that cross section, there should be a set of forces which are counterbalancing this one. Okay, so F vector will be what? First of all, there will be a plus 350, right? 350 I hat. Then it will be a plus 375 j hat. Oh, by the way, I did not write the units here. Plus 375 j hat and then minus 450 k hat with Newton sitting outside. Okay. Now, you tell me for sigma xx, what is the normal force? The coefficient of this. Okay, that is the force which is normal to the plane. So 350. Okay. So what I'll do is, instead of writing like this, later on it will be confusing to devise. Yeah, so I will call this, so this one I will call N, this one I will call Vy, and with the minus sign, okay, I will call this as Vz. Okay. So here it will be N divided by A. A is what? Pi r square. Okay. This is positive or negative? Just tell me. Positive, right? Now my suggestion to you is, do it very, very explicitly. Whatever the thing is here, you know that this is positive and this is going to be tensile. Nevertheless, write like this. Okay, write like this and put a positive sign. You will thank me later. Next, the contribution from the flexure. Now, flexure means what? Some my by I. Okay. Now see, when you are looking at the point A, which of these moment components will be contributing towards generating the normal stress due to the flexure at point A. Mz. Okay. So just see the Mz, that minus 75, that is oriented how? That is minus 75 k hat, right? So minus 75 k hat is oriented in this fashion. Okay, this is the orientation. So if you take your thumb like this, it is like this. Okay, it is like this. So your fingers, the other four fingers, they are going to curl up and move out like this, which means that at the point A, due to this Mz, it will be coming out. Okay, it will be tensile. But the point of confusion is that there is a minus 75. And back when we were doing our theory, the sigma was with a minus my by I. So clear your head of all these things. Okay, we have chosen to give pain to ourselves. Okay, we will take the pain full blooded. Okay, so what we'll do is we will write here mz, and we'll put this absolute sign around it. Okay, then we'll write this y. What is the y here? Y is the radius, this radius. Okay, this radius divided by I is actually just I, same thing for a circular cross section, but just to clear it up, we'll write as iz, meaning that it is the second moment of area about the z axis, just to state it explicitly. Now please note that I have still not put the sign over there. The reason is I want to compare with this thing which I have already written. The first one was tensile, the second one is also tensile, therefore it is plus, and overall this sigma xx will come out as tensile. So even without doing any calculation, you can actually write that this is a tensile thing. Okay, and my suggestion is that in your answer, you write that tensile thing. Okay, make it fully explicit. All that you have to do now is place the values. Okay. Next, for tau xy. Everyone look, please put down your pen for half a minute, 1 minute and listen. Tau xy, okay, tau xy will be generated by what? Which force? No, I'm talking about the transverse shear now. Torsion I will come. First, the transverse shear. Transverse shear, it will be because of the Vy force or the Vz force? Huh? At A, tau xy is what? This x, it only represents the unit outward normal to the plane that we are considering. So it is not giving us any real information regarding the direction of the shear stress. It is this y which is giving us the real direction. Okay, so the tau xy will be pointed in this way, either upward or downward, but in that oriented along the y direction. So oriented along the y direction means the contributing thing, the source of it will be the Vy. Okay, it will be the Vy. Now let me just write the thing. Okay, Vy q by it. This is the formula. But you note, where are we sitting? We are sitting at the top. Okay, now at the top you have a tau xy, but if you look at the complementary shear stress which is on the surface of this thing, so what I mean to say is, so you look at this thing, this is your cross section which you are looking at. We are looking at this top surface on this plane. At the top, whatever the value of tau xy is, the same value will be there for the tau yx, which will be there in the little element here. Okay, so they are like brothers and sisters. Okay, in fact, like they are like twin brothers or twin sisters. So tau xy and tau yx are the same. Now on the top surface, it's a shear free surface. Okay, it's a shear free surface. So tau yx is 0. So tau xy must also be 0. Now why is tau xy 0? Tau xy is 0 because our q is actually 0. You note that if our point of interest was not this point A, Rather, it was somewhere here inside. Then we would have drawn a line like this, and then we would have taken this area. Okay, we would have taken this area. That area would have contributed a some value of the Q which we would have utilized here. But now this is not the situation. We are not sitting inside, we are sitting at the edge of the cross section. So there the Q is actually 0. Okay, so here this entire thing is actually 0. So the contribution to the tau xy because of the transverse shear is actually 0. Okay, now you may think that okay, Vz is there. True, Vz is there, but Vz is not going to contribute to tau xy. Vz is going to contribute to this tau xz. So we'll consider that when we'll come to that. Next, we are going to consider, so remember, within each tau, we have to consider the shear stress due to the transverse shear as well as due to the torsion. Don't forget this, both due to Tr by J as well as due to Vq by It. We have just finished the Vq by It, now the Tr by J. Now you see, what is the torque? What is the torque here? Torque is basically a moment. So on this section, the torque will be what? The torque will be something which is oriented like this, with the thumb pointing outward or inward. That is what we have learned from the torsion thing. Now you look at this M thing, M vector, and you tell me which component is the torsion component. Yeah, so the one which is with the I hat, that is the torsion. Okay, that is the torsion. And very explicitly speaking, since it is minus 28.125, it is actually going into the plane, which means my thumb should go into the plane, which means the torque is like this. This is very important to see. See, in that formula, you don't have to worry about all of these things, the yesterday's formula. Automatically, the vector thing takes care of it. But since we have chosen to take all this pain, we have to do it. Okay, so now our fingers are curling like this. Now, fingers curling like this actually has a significance. What is the significance? In which direction the shear stress will be. So, if my curling is like this, the shear stress will be in this direction, which is negative to the z-axis. Okay, so at the point A, the shear stress contribution due to the torsion will be directed along the negative z-axis. Okay, which means that in the tau xy there will be no contribution. Okay, in the tau xy there is no contribution. Next, tau xz. We have not yet gone to point B. We are still sitting at point A. Now at the point A, there will be first of all a contribution due to the transverse shear. This time the contributing source is this minus 450. Okay, so we write this Vz by It. Now you tell me very formally, this I is Iy or Iz? It is same, I know, it is same, but we want to be very, very explicit and clear about it. It is Iy or Iz? It is actually Iy. Now, all of you, like yesterday, all of you tilt your head to your left. Okay, and see the Vz actually acting like this. Okay, Vz is in a minus 450, so the force is acting like this. So if you just imagine that since you're rotating your head, okay, tilting your head, it is a force which is like this, and at the neutral axis, which is the y-axis, you have this point A. Okay, so this A is actually at the neutral axis. Okay, so you have to rotate your entire thing like this. So just think of it like this, that this is our y and this is our z. Okay, and our Vz is acting downward and our A is here. So this Vq by It is actually here, pointing downward. So this is actually the Iy. Now you put this thing, this Vz. Okay, the absolute value. Okay, fine. And now you put the sign. Okay, you tell me what the sign is. Is it sitting at A? Is it in the plus z direction or is it in the minus z direction? Vz is in the negative z direction, so minus z direction. Okay, so therefore this one will be coming with a minus. Okay, in a very explicit fashion. Next, the tr by j contribution. Tr by j contribution, again to reiterate, our mx is minus 28.125. So it is like this. Okay, rotating in a clockwise sense. In a clockwise sense means at the point A, the sense will be in the rightward sense. The tr by j shear stress will be in the rightward sense. Rightward sense means what? Negative z direction. Okay, which means that it will be minus mx modulus r by j. If you write like this, then because see, either you do it within a automatic fashion with the plus minus algebraically, or you take the pain to do this. Okay, choose any one, don't mix it up. Okay, if you choose to do like this, it will be absolutely fine. Okay, no problem. So it will now come. Okay, the answer will come. But, and this also your seniors have done, they do everything correctly, shear stress, all the plus minus business, perfect answer to the third decimal place, and then finally they write C. C means compressive, because there is a minus sign, and I have taught them in class that there is a plus or minus, so it is tensile or compressive. But in shear stress, what is tensile and what is compressive? Okay, don't do these things. Okay, like my heart bleeds when I see these things. So, okay, please do not write tensile or compressive. The only thing this minus is indicating that it is in the z direct, the negative z direction. Okay, for the normal stress, with your Hertz content, you write T, C, all these things. Okay, next for this point B. Yes. Here. So our sense of the torque is like this. It is in this direction. Here, there is no shear stress which is acting like this. Okay, so the only contribution from the torsion will be in this direction. Okay, like this.
Provided this geometry, there will be no torsion, no shear due to torsion. This tau xy due to torsion. There will be any tau xy.
So if you have this kind of a circular geometry,
Not due to
then
only due to torsion.
only due to torsion it is not possible to have the tau xy thing. Okay, but don't remember it like this, because I mean the coordinate axis may be changed and all these things. So just remember it, like do the problem as it comes to you. Next, for the point B, again we will write these things: sigma xx, tau xy, and tau xz. Systematically, if we do it, there will be no problem. Again, tell me, sigma xx contribution will be what? Again, that n by a. There is no difference, n by a. This one will be plus. Next, what will be the contribution due to flexure? First of all, let us identify what the thing is, and then we'll figure out what the plus or minus thing will be. We are sitting at the point B. Now you keep your tilting your head leftward only. Na? Okay, so this picture basically. Okay, so where are we sitting? We are sitting here. I mean, we are focusing our attention over here. This is the point B. Now for the flexure, which moment will be the thing? It will be the my. Plus or minus is a separate thing, but my. Okay, so either like this or like that. Now let us check what the my is. Check what the my is. My is minus 63.75. Okay, 63.75 is not the important thing right now. The minus is the more important thing. Now minus means it is in this sense. Okay, the moment vector, it is like this. It is like this means my thumb should be pointed along this arrow, which means the other four fingers are curling into the plane of the board. Curling into the plane of the board means what? What is the sense? It is compressive. Okay, so we will write it first of all with the y. My, we'll put an absolute value around it. my. So this is r, okay, divided by what? Divided by iy. And this thing is into the plane. Okay, it is a compressive contribution. So this one will be with a minus. Now, from before you cannot write whether this is tensile or compressive. You have to put in the values, see whether it comes out as plus or minus, and then write tensile or compressive. Okay. Next, tau xy. Look at this picture only, or tilt your head to the left and look at this picture, whatever is convenient for you. So at the point B, we are interested in finding out the tau xy. First of all, due to the transverse shear. So let us write the transverse shear thing. So it will be the Vy modulus Q divided by, what will it be? Iyt. Okay. What is the Vy? Vy is here. Okay, plus 375. Plus 375, so don't jump to conclusion just because it is plus, so put a plus, not like that. So check for yourself explicitly. So Vy, it is like this. Okay, it is like this Vy. So if it is like this Vy, then just a second. I think I made a mistake. This should be Iz, no? Okay. So this is the Vy. Okay. The axis that you are looking at is this axis. Okay. This is the axis. Now, Vy is positive, we understand, but the shear stress due to this positive Vy at the location B will be in which direction? You just tell me right or left. Vy is plus 375, so it is directed like this. Okay, so at the point B, the tau xy will be left or right? Right side. Okay, right side means it is oriented along the plus y only. Okay, so it is plus. Check whether the q is contributing 0. It is not. Okay, it is very much not. Q is not contributing 0, because what is happening is, like, so this is your q, or here this is your q. Okay, this will be actually 2 by 3 r cube. All right, what will be the value of the t? What will be the value of the t? Thickness. It will be the diameter. It will be the diameter of the cross section. Okay, so please remember these things. Next, the tr by j. Okay, tr by j. So again, which is the torsion? It is the mx component, again that minus 28.125. So over here, you see, you look at this picture only. Again, this thing is like this. Nothing has changed from before, because mx is mx. So it is like this. Now when it is like this, you focus how my fingers are curling at the location B. So it is in the clockwise sense. Clockwise sense means here it is pointing upward. Okay, it is pointing upward. Is it not? Everyone, please convince yourself. Is it pointing upward or not? If I curl my fingers like this with my thumb into the board, then at B the direction is upward. ठीक है? So all right, that plus that I have just written, it is respecting the fact that upwards means along the positive y. Only that. Okay? Yes. So when we are looking at tau xy for the point A, this you see now why this is thing. Okay. So here the Vy is like this. Okay. This transverse shear is occurring about which axis? It is about this axis. Okay. and our location is what? At the top of the cross section, right? But when we are looking at the point B, this is the point B. Then again, this is the thing. The axis is this. My point is here. For this point, what kind of a cut do I need to take in order to find out the Q at that location, parallel to the axis under consideration? Axis is Z axis, so my cut is along the Z axis. So when I take my cut along the Z axis, the entire part of the cross section above that cut will contribute to the Q. It is not zero. The thing that I think you are confused about is that this point is also at the edge of the cross section. So axis should be different. So here you tell me which shear stress will be zero here. Not associated with the torsion, but just associated with the transverse shear. So if you consider the tau xz, okay, tau xz is zero here. Why? Because again, if I take my bottle, I take my bottle here. So this is the point B. Here the tau xz is in this direction, but there is a tau xz here also. No? Okay, so that tau zx actually is zero. So its twin brother is also zero. Okay, so again, this is Vz Q by Iyt, and this is zero. Why? Because the Q is zero, as I have just now explained. Okay, so this entire thing is zero. You think about it for a few seconds, everyone. This is extremely important. You can look at this diagram. This will probably be easier. So here, the Vz is acting downward. Okay, the Vz is acting downward, but the location of our point of concern is at the edge of the cross section. So the Q that you are going to get is because of this cut, but there is no cut there. Okay, it is at the top edge of the cross section. So had the point B not located at this top, rather somewhere here, then you would have taken a cut like this, then that little amount would have contributed some non-zero value. Okay. Next, due to the TR by J. Now, see, we are looking at the tau xz. So we are looking at the shear stress contributions in the Z direction. We have already seen that in the tau xy, the TR by J is already contributing. So here again, just for convincing ourselves, we curl our hand. And if we curl our fingers like this, we'll see that it is pointing upward, but nothing is getting pointed in the Z direction. Okay, so there is no contribution in the Z direction due to the torsion. So this is zero. Please do not take it as a rule of thumb that just like you have seen tau xy is 0, 0, and here also tau xz is 0, 0. Please do not jump to conclusions like this, that for one point, if it is one of them is 0, 0, the other one, for the other one it will be 0, 0. Okay, don't do any of these shortcuts. Yes.
Sir, will it still by MR by I term of that tau xy is 0 for A?
For B or A?
A.
For A. For A, which one? This one or this one? Tau xy?
The second 0 term.
This one, right? Sure. So at A, we are looking at the, so which one is the direction we are interested in? The Y direction. Okay, Y direction is this one, but our torsion is like this. So it is actually in the Z direction. Okay, there is no contribution in the Y direction. That's why. So torsion is always in that tangential direction. Okay.
So when we are finding the stress along Y direction, we are taking the axis as Z, and when we are finding the stress along Z direction, we are taking Y.
You are talking about the transverse shear. This one.
Yes.
Yes. So this Vz is like this. Vz is like this. This Vz is associated with which moment? So remember the relation that V is equal to dm dx. There is a, I mean, you know, and you may have forgotten. Okay, so V is equal to dm dx. So which moment are we talking about here? Moment about which axis? So moment about the y-axis. So it is this kind of a flexural moment. That flexural moment has the connection with the Vz. So they are like counterparts to each other. Okay. Yes.
So then, for B, how is it like? How are we calculating it? MR by I.
Here, this one. So here, you'll again look at this thing. Okay. So now, when we are looking at the tau xy. Okay, tau xy means y direction. Y direction means upward. Okay, and our torsion is also like this. So when my fingers are curling, so they are curling like this. No, so when they are curling, so they are reaching here. In which direction my fingers are pointed? Upward. So it is in the y direction. It's good you are asking questions. You should. Anyone has any confusion, please don't be embarrassed to ask. I am on camera, right? So I'll tell you how shameless I am. Okay, let it go on record. Don't edit it out. Okay, so let it be on record. So every time I teach this, before coming to class, I actually go through it. Okay, it's not that, I mean, you pull me out from any in the middle of some activity and then I can just spontaneously tell this, not like this. Okay, this thing is actually complicated. You need to, wrap your head around it a little bit. Okay. So there is nothing to be embarrassed about, not understanding, not getting your head to wrap around it the first time you hear it. I have been hearing it since when I was a student. When I am a faculty, I am teaching it, supposed to be an expert. Then also I have to be very conscious about it. There are certain chapters I can teach even in my sleep. Okay, you hold a bullet to my head, then also a revolver to my head, then also I'll be able to teach. This one, no. This is different. Okay, so if you're all on the same page more or less, we can proceed from here. Now you probably will appreciate uh, the usefulness of the formulas I shared yesterday. But it is good to know this. Okay. Yes.
Explain the first term in
This one. This one. Okay. So we are looking at the point B. We are looking at the point B and we are looking at the contribution from the transverse shear. So Vy is like this. Okay. Vy is like this. Should it be a minus? Huh? Oh, sorry. Vy is plus. Okay, Vy is plus. So that's why. Okay, Vy is pointed upward. So tau xy will be pointed upward.
why we are writing IZ.
Why we are because see, just as he was asking, right? So when you are talking about the Vy, this thing, it is connected with which flexure or which moment associated with the flexure? It is about the z-axis. Is it not? If you have any confusion regarding this, just do one thing. In your rough column, everyone look at this. If at any point you are confused about this, just go to your rough column and draw a simple diagram like this. This diagram you are all familiar with. So here the neutral axis was like this. Okay, and your loading was like this. Okay, and your moment was like this. So this moment is about what axis? It is literally about this axis, no? Okay, and you give these names. So let this be the y-axis and this be the z-axis. So everything will become clear. Okay, so this force is along the Vy and the axis is along the Iz. Okay. The problems of tutorial sheet 8 are not exactly short. So in the 10 minutes that I have, what will I do? That is the issue. I wanted to discuss this question number 14, but I don't have enough time for it. Where is the sheet? Acha, let's do one thing. You look at question number 8. Look at question number 8. Tutorial sheet 8, question number 8. The cylindrical portion of the compressed air tank shown is fabricated of 8 millimeter thick plate welded along a helix forming an angle beta is equal to 30 degrees with the horizontal. Knowing that the allowable stress normal to the weld is 75 megapascals, determine the largest gauge pressure that can be used in the tank. Okay, basically you have to find out such a pressure which will be just below the, which will ensure that the stresses developed in the wall of the pressure vessel will be not exceeding that weld strength. Okay, and please do not think that this is just like a Beer and Johnson kind of problem. Okay, I mean probably it is from Beer and Johnson, I don't remember, but this kind of a fabrication is actually used in the industry. From long strips of metal, they actually wield it in the form of a helix and construct the pressure vessels. Okay, this is a standard technique. Not the only standard technique. There are some fascinating videos in YouTube about the welding of pressure vessels. So you can probably watch those things. Okay, so what we'll do is, instead of tilting our head, we will tilt the picture. Okay, so it will be easier for us. So we will draw the picture like this. Okay. The helix angle, so our helix is like this. So I will draw only one seam of the helix. Okay, this is one seam of the helix, and this is the beta that is given. Now question is what? Question is pressure. Pressure we have to find out. But how do we connect all of these things together? Like, so what are the things that we have actually learned in the context of pressure vessels? We have learned about the hoop stress, the sigma 1, and we have learned about the longitudinal stress, which is sigma 2. So suppose we we focus our attention at any point along the weld. So at any point along the weld, so maybe we'll focus our attention here. Okay, so over there, the stress that we are going to have, so let's say this is the point. We know this value, this is the sigma 2, and we know this value, this is the sigma 1. Sigma 1 is equal to PR by T, and sigma 2 is equal to PR by twice T. Okay, you can check back in your notes. All right. So sigma 1 is equal to PR by T, sigma 2 is equal to PR by 2T. But the helix, the weld is not along any of these things. Okay, the weld is not like this, the weld is not like this. Rather, the weld is like this, which means that the stresses, this is the stress which we are actually interested in, this sigma dash. this sigma dash, because it is, the weld is joint like this. If the pressure is too much, then the weld will not be able to sustain that joint. Okay, it will just come apart. So if this sigma dash exceeds the value of the allowable weld strength, then it is going to come apart. Okay, it is going to be a disaster. So that sigma dash is what you have to find out. So here you note that this is beta, which means this is 90 degree minus beta, which means that this is beta. Now, whatever the actual engineering situation was given to us, we have now translated that into the language of what we know from from the stress transformation chapter. Okay, so now it is just a question of using the appropriate formulas. So this sigma dash will be like our sigma x dash x dash. That will be equal to sigma x. Tell me the formula. What was that? Sigma xx plus sigma yy by 2, that thing. Rohit, it is getting captured. No? Okay, now we have to be very careful. Please do not, I mean, this is where mistakes happen. Like our brain processes it like this, na, ki x maps to 1, y maps to 2. But here it is not like that. You see, in this x direction, it is 2. So sigma xx is actually sigma 2. Sigma yy is sigma 1. Okay, so please be careful about this. What is tau xy?
0.
Yes, confidently say 0. Tau xy is 0. Okay. Now, sigma 2 expression you have in terms of PR by twice T. Sigma 1 you have in terms of PR by T. R and T are known. P is not known. What is this sigma x dash x dash? This is the sigma allowable. Okay, this is the sigma allowable which is probably given to us. Is it? 75 MPa. Very good. 75 MPa it is given to us. Okay, so quickly do this problem. Substitute all these things. Sigma 2 is at PR by twice T. रोहित बंद कर दो.